All right, let's put it all together with one last example. So discuss the curve y is equal to x over x squared plus 1 with respect to the intervals of concavity. List and classify any points of inflection. So for part 1, we're going to do the derivatives. If f of x is equal to x over x squared plus 1, then I'm going to use the quotient rule to solve f prime of x, low d high less high d low, draw a line, and square below. I'm going to simplify this. Oh, don't forget to square that denominator. And I'm going to get that f prime of x is equal to negative x squared plus 1 all over x squared plus 1 squared. I can factor out the negative. Doesn't really make a big difference because now I'm just going to take that and I'm going to do my second derivative. The second derivative is going to give me x squared plus 1 squared times the derivative of the top, which is negative 2x, minus top, negative x squared plus 1, and I need to use the chain rule now to do the derivative of the bottom, which is going to give me 2 x squared plus 1 to the power of 1 now, and then the derivative of the inner, which is just going to give me 2x, all over x squared plus 1 squared, and then I have to square it again. Now we do the simplifying. So if I have negative 2x and x squared plus 1 squared minus 4x, negative x squared plus 1, and x squared plus 1 all over x squared plus 1 to the power of 4, then I can factor out negative 2x. I can factor out a x squared plus 1, and that's going to leave me with x squared plus 1 plus 2 negative x squareds plus 1 all over x squared plus 1 to the power of 4. But now I can see I have a common factor of x squared plus 1 on the top and on the bottom, so I'm going to take away 1 from each of those. Going to keep going. And I have negative 2x and x squared plus 1 minus 2x squared plus 2 all over x squared plus 1 to the power of 3. And my f double prime of x is going to equal, well, I'm probably going to pull a negative out of there too, so I'm going to call this 2x, x squared minus 3, all over x squared plus 1 cubed. All right, we did our derivatives. Let's carry it forward to do our significant numbers when f double prime of x is equal to 0, or f double prime of x is undefined. So when it is equal to 0 from the numerator, I'm going to get 2x, and x squared minus 3 is equal to 0, which means that x would equal 0, or x squared minus 3 would equal 0, where x squared would equal 3, and x would equal positive or negative root 3. In my denominator, if x squared plus 1 cubed is equal to 0, x squared plus 1 would equal 0. When I move the 1 over, it's going to become negative 1, and if I try and square root it, there is no solution. So the does not exist, or pulling from the denominator, doesn't work. So now I have the 3 significant numbers. X is equal to negative root 3, x is equal to 0, x is equal to positive root 3. And we're going to put that into our chart. So we have our intervals. We're going to go from negative infinity to negative root 3. We're going to go from negative root 3 to 0. We're going to go from 0 to positive root 3. And we're going to go from positive root 3 to infinity. We have our factors: 2x, x squared minus 3, x squared plus 1 cubed. And we have how that's going to apply for our second derivative and what that means for our original function. So when I pick numbers to sub in, like negative 5, negative 1, positive 5, then I see that 2x goes from being negative to negative to positive to positive. X squared minus 3 goes from being positive to negative to negative to positive. And when I square the numbers and then cube them and add 1 to it, it is just always positive. For my second derivative, I'm going to have a negative, a positive, a negative, and a positive, which means that I have concave down to concave up to concave down to concave up. Because it is changing from concave down to concave up at each of these points, then each of those points is going to be a point of inflection, which means that from what I see here, I'm going to have a point of inflection at x is equal to negative root 3, x is equal to 0, and x is equal to positive root 3.